today. Thank you very much for being here this beautiful day outside. So, Thomas has promised that he's going to give us a very exciting talk just to counter that. And so we're very happy to have him here today. He's coming from Munich, and a lot of you know him already. He's got a lot of different awards, and he's in charge of, for example, the Excellence Cluster, and I'll say the origins and structure of the universe. And he's also leading a couple of projects, among them one on gravitational wave astronomy. He got several awards, among those the Otto Hahn Medal and the Heinz Billinger Prize for Scientific Computers, and has done a lot of outreach as well, as I'm sure we'll see in this talk. And so we're very happy to have him here today, and he's going to tell us how we're unraveling the explosion mechanism of massive stars.
Thank you very much. Very kind introduction and the hospitality I've experienced here. It's not my first visit to Heidelberg, and I know the place, I know the people, of course, but it's my first lecture here in this wonderful auditorium, so it's a real pleasure, and hope we can compete at least for 45 minutes with the weather conditions, which have improved significantly. Lisa has promised a lot. I mean, I will tell you what we are going to do and what we are currently doing in order to solve a long-standing problem, namely how supernovae explode, how the majority of them explodes. My talk by far cannot cover all types of supernovae, all explosive phenomena of massive stars, so I will constrain my talk to 99.9% of these cases which explode at the end of their lives. This is research funded by currently 2 programs where we also have manpower financed from, and also we got a lot of computer time I will show you later on. So that's the kind of phenomena which we are considering. That's actually a remnant of one of these explosions, massive star explosions, stars which disperse heavy elements at the end of their lives. And what you see here, and this is the interesting aspect of this image, a 320-year-old supernova remnant of this Cassiopeia A supernova, that the ejecta are very asymmetric. There is no indication of a spherical ejection of matter, and you can, if you look closely, also see this compact object at the center, which was only discovered with Chandra, with the resolution Chandra. The X-ray satellite could provide an X-ray source. It's a cooling neutron star, and actually you can follow its cooling history nowadays, and this tells us something about the equation of state in a hot neutron star. Okay, so this is the objects. This is another famous example which I cannot hesitate to show. The supernova 87A exploded in February 23rd of the year 1987A, is now seen as a remnant here, expanding ejecta cloud inside of this ring structure, and you can also see 2 faint rings towards the northern and southern polar directions. This ring system is a relic of the progenitor evolution. The ring system was formed about 20,000 years before the star exploded, so it has nothing to do with the explosion itself, but what we are interested in is this elongated ejecta cloud, which shows also deformation. In case of, say, supernova 87A, we had the interesting opportunity to, for the first time, and so far the only case, to discover 2 dozens of neutrinos in 3 underground laboratories. And what these neutrinos told us is that a neutron star was born in the supernova and at least existed for a period of something like 12 seconds. It was showing a neutrino cooling signal as predicted, roughly with properties as predicted already by models at that time. So a really strong confirmation that a supernova gives birth to a neutron star. This is the outline of my talk, and I hope I can cover most of it. I'm not sure that I will touch a lot of the last issue. I will give you an introduction into the phenomenon, and I will particularly motivate what we think is the paradigm of explaining the explosion, the neutrino-driven mechanisms. So supernova explosions are tightly linked to the neutrino emission, which I showed you on the previous slide of this newly formed neutron star. We have good sets of models now in 2 dimensions, and we are with big efforts pushing forward into the 3rd dimension of modeling, which is a very hard and challenging task. And if I have time, if time permits, I will also address a few of the observational consequences of these neutrino-driven explosions, which we are currently trying to explore with gradually more sophisticated models. much of the subject can also be covered by my book here, a little semi-popular book, which you can read if you're interested in it. There are 2 scientific reviews articles I wrote last year, so there's a lot of literature also on the subject, and in particular covering the latest evolutions, the developments in the field. The supernova research done in my group is a group initiative. I'm actually working on 2 different subjects. These I didn't mention. It's on the one hand supernovae, but on the other hand gamma ray burst scenarios, neutron star mergers, neutron dynamical phenomena around neutron stars. And there's students, master, PhD students, as well as postdocs. Marcella has left for Darmstadt, and Bernhard and Andreas Brauser are also going abroad now for postdocs. This is now going to the scientific part. This is the overview slide I can present you where I summarize the evolved stages of massive star evolution. We won't touch too much of that in this talk. I just want to give you an impression where we are in this space of central density here in logarithmic units, and here central temperature of the star. So the evolution tracks of massive stars go roughly like the temperature to the cubed proportional to the density. So they are nearly straight lines. In this diagram, I think this device. And then at the end of the stellar evolution, the stars run into these instability regions here at the edges of the diagram. And what we are interested in here in this talk is in particular this upper left part of the diagram. This here is a region where very massive stars, maybe 100 solar masses or more, become unstable and in the end gravitationally collapse to either a neutron star or a so-called pair instability supernova. The physical mechanism of this phenomenon is very well understood, so there is not much question that these cases, how these stars could explode. But here in these regions, here in the upper part, we have 2 instability mechanisms which then initiate the collapse, and the ongoing evolution towards the supernova is still a puzzle and is still to be resolved. There's on the one hand the iron-helium photodisintegration, I will mention in a minute again, and on the other hand rapid electron captures. We'll come back to that after the next slide. So this here is an image of a schematic image of how a massive star, a star which has gone through all stages of burning, central burning, looks at the onset of central instability, of core instability. So the star has the so-called onion shell structure, where a very evolved core, an iron core, can also be for lower mass stars an oxygen near magnesium core, is surrounded by shells of successively lighter elements, silicon, oxygen, carbon, helium, and the star still can have a hydrogen envelope. If the star strips hydrogen and helium, the supernova type, the observational type can vary, but the internal structure in the central parts is more or less always very similar, like this kind of onion shell structure. We will concentrate our attention in the ongoing talk to the inner region, where the core is sitting at the center. And here is the enlarged view of the central region where the iron core is shown at the onset of instability. The gravitational instability is triggered when the iron core, which grows in mass by a silicon burning shell around it, when this iron core gets close to the critical Chandrasekhar mass limit. It's not exactly the classical Chandrasekhar mass limit because this core is hot. This core has some physics which deviates from the Chandrasekhar theory. And in particular, it's on the one hand the temperature, the high temperatures in these core, which start to disintegrate the newly assembled iron into alpha particles and partially free nucleons. And on the other hand, the electron captures, the fact that protons inside of nuclei mostly start to capture the electrons. Both of these processes lead to gravitational instability when this core is roughly of the mass of a Chandrasekhar mass. What happens then is a dynamical implosion on a time scale of less than a second. So this is really a dynamical phenomenon which has to be followed by time-dependent simulations where you can follow this infall until in the center a nuclear matter density is reached and a neutron star begins to assemble. So the densities even exceed nuclear matter densities. the maximum densities at the moment of what we call core bounds can be up to 2 times nuclear matter density. And what then happens is that the equation of state stiffens, and that means that it resists further compression, and it starts the neutron star, the seed nucleus of a neutron star starts to assemble. Pressure waves moving out from the center steepen into a shock wave here at the transition of the subsonic to the supersonic infall region, and the shock wave starts to propagate outwards in mass as well as in radius. Until maybe some 10 years ago, people still had some hopes that this shock wave created in this core bounce mechanism would initially initiate the explosion more or less immediately. This prompt mechanism, this prompt explosion mechanism is a purely hydrodynamical phenomenon. What instead was shown by numerical simulations mostly, you can do order of magnitude estimates also on a sheet of paper, but you cannot be sure that your quantitative analysis is really reflecting the complicated nonlinear physics in the supernova core. So simulations showed that this shock wave stagnates well inside of the iron core. It loses energy mostly by disintegrating iron into the free neutrons and protons, consuming about 8.8 mega electron volts per nucleon, and this taps a lot of energy. Actually, it stores it in a free nucleon gas, and this energy drain is taking away the kinetic motion, the kinetic energy, the outgoing expansion of the shock wave, and leads to a stagnation of the shock at a typical radius of about 100 to 150 kilometers only. So well inside of the iron core, this shock is trapped and no explosion happens. And that was the puzzle which emerged from the first, second, and third generations of supernova models, and is to some extent still with us. What helps reviving this shock wave? What makes it alive again? What drives it outwards and re-accelerates the shock wave into an explosion? Well, what we think now, after decades of hard work, is that neutrino healing is a clue, and how this is supposed to happen is shown on this cartoon slide. You have this neutron star assembling at the center, and the neutron star is initially extremely hot. It reaches maximum temperatures after some while up to more than 50 mega electron volts. So that means of the order of something like 50 times 50 gigakelvin. And these temperatures lead to a copious production of neutrinos, and the neutrinos stream or diffuse towards the neutrinosphere, which is the another one of the photosphere of the sun, before they start to stream away. But they don't stream away completely freely. With a finite probability, and actually a non-negligible probability, the neutrinos still have a chance to interact in this region between the neutrinosphere and the shock wave. The shock wave shown here, this is a device. The device I think is giving up. The battery is probably low, I'm guessing. There's no battery in there. So you see the shock wave indicated there, a radius of about 200 kilometers, and this neutrino flux from the neutrinosphere is absorbed partially of the order of 10% absorption probability on free neutrons and free protons, shown here in the two types of reactions, and this deposits energy. And first simulations in the 1980s done by Jim Wilson at Livermore have already shown that if it's strong enough, the energy deposition, if it's strong enough, it can help reviving the shock and driving the shock further out, reviving it into an explosion. However, the true story is very, very difficult to quantitatively address. We now know, after some work in the 1990s, that hydrodynamic instabilities play a role and are actually crucial. No one-dimensional model for, thank you very much, no one-dimensional model for iron core progenitors yields explosions in spherical symmetry. So what we are relying on is the help of these overturn instabilities, which actually extend the time matter here falling through the shock. Matter can stay in this heating layer between what we call gain radius and shock front. And if matter here is kept for a longer time by these convective instabilities and another instability, more newly named the standing accretion shock instability, I will come back to that later, if these instabilities conspire and help keeping matter longer for an extended time in this heating layer, it can really help for the explosion. Here you see another cartoon image of the situation where the instabilities are already shown from a simulation. Here you have the proto-neutron surface with the neutrino emission indicated by these wiggled arrows, and here you see these instabilities, convective instabilities growing between the neutron star surface and the shock wave. The infalling material here is damping the expansion of the shock, so the whole situation here is exposed to two constraining issues. On the one hand, the damping of infalling matter, which prevents the shock from expansion. On the other hand, the push from the neutrino-heated bubbles. And what's winning is a quantitative question. For two more slides on what happens if the explosion proceeds successfully, here I already assumed or indicated what happens when the shock wave is pushed hard enough by these bubbles. It would start running outwards into the oxygen, silicon-oxygen layers, and then behind this shock wave, nickel would be nucleosynthesized, would be explosively synthesized by burning of oxygen or nickel or silicon, and this nickel being later on injected in the explosion is actually the nickel which makes the supernova shining bright for months and actually years. It's the decay of radioactive nickel freshly synthesized in the explosion, not being present yet in the collapsing core. Now, about half a second later, this instability region has decoupled from the neutron star surface and is pushing outwards and is moving away from the explosion site in the accelerating explosion. And what happens then is that the neutron star surface still loses mass at a lower rate in the so-called neutrino-driven baryonic wind. And this neutrino-driven wind is an interesting site for heavy nuclei nucleosynthesis. In particular, we think that there is a possibility of synthesizing N=50 nuclei, strontium, yttrium, and zirconium. And for some while, there was a hope to get even R process elements from this site, which, however, doesn't appear likely on the basis of the new models we are doing by computer simulations. Here's a bit more of the physics which determines the neutrino-driven explosion mechanism, the neutrino heating and cooling. If you don't want to follow these equations, you will not lose a lot of what is coming later on. I just want to give you a more quantitative feeling of what plays a role, and at least for the ones in the audience who may be interested in the neutrino physics, the answers are here on the slide, or short answers are here on the slide. So the heating mechanism mostly works by electroneutrino absorption on free neutrons and antineutrino absorptions on protons, and the heating rate is given here in this formula, which I have coined in where I factorized in the neutrino luminosity in certain units. I don't know what's going on. The battery is probably, maybe it doesn't like to be held up right for some while, I don't know. You see the neutrino, well, it's very difficult to explain that without pointing. The neutrino luminosity, the temperature to the square coming from the energy dependence of the absorption cross sections, and then we have a factor 1 over r to the minus 2, or 1 to the over r to the second power, because of the radial dilution of the neutrino flux. Competing with the heating is the neutrino cooling, where the temperature of the fluid is relevant to the 6th power. And once you know that the temperature outside of the neutron star roughly declines like r to the minus 1, there's another device, so I can try this one. Thank you very much. Try this one. Yeah. Once you know that the temperature declines roughly like r to the minus 1 in the region between the neutron star surface and the shock, while this heating term only declines like r to the minus 2, you immediately recognize that there must be a gain radius outside of which this heating term wins. You can then estimate the mass which is heated by going to your simulations. You find that it's roughly 1/100th of a solar mass, or maybe even a few hundredths of a solar mass. Multiplying that with a heating rate per gram, you will find an energy which is very interesting. Once you know that a canonical supernova explosion energy is of the order of 10 to the 51 ergs, canonically named 1 pho or 1 beta nowadays, you notice that within a fraction of a second you can deposit an energy by neutrino heating which comes close to a supernova explosion energy. You can also estimate the time scale matter is staying in this heating layer, typically about 1/10 of a second, estimated here by dividing the mass in the gain layer and divided by the mass accretion rate. So you get this number here to be about 0.1 seconds, and then you end up with a number which is close to an explosion energy of a supernova, of a typical supernova.
Since you're going technical here anyway, so
yeah.
your pictures imply, I mean, that the explosion is not spherically symmetric.
Yes.
And the region in which
yes.
the neutrino energy gets deposited is inhomogeneous, etc., etc. So there's some big operative transport. How does it go in? Because it must matter whether that gets deposited in the
Absolutely. Thank you for your question. It enters here. So this is the dwell time. That's the reason also why I coined this in this formula, because this can be measured independent of 1D, 2D, or 3D simulations. It's the mass in the gain layer which mostly is changed by the multidimensional phenomena which keep matter longer in the gain layer, and therefore the mass in the gain layer is building up to a larger value. So
it still looks very one-dimensional. You talk about layers while...
Well, actually, I mean, when you apply this analysis here to your simulations and calculate these numbers, you can match the numerical results very well. I will show you, of course, this is only a back of the envelope calculation which gives an order of magnitude estimate. I don't say that the answer is here. The answer is, of course, a quantitative, needs to be given by quantitative simulations. So that's written here. Self-consistent multidimensional models are required to provide you with a quantitative answer. But what I wanted to show by this technical slide, as you name it, it's just that the numbers could work out in the right order of magnitude. Yeah?
And so these are not just 2D hydrodynamics, but the neutrino transport is also in 3D.
Can you wait for 5 more minutes? Then you will get all your answers. I'm still in the somewhat preparatory part because I don't want to jump into the details immediately. So I have to bother you, unfortunately, with one more slide in order to show you the problem which we are really facing. This slide is this one. This comes from a simulation, but you can also do that by semi-analytic means, where you can actually summarize the delicate competition which the supernova physics is exposed to in the supernova core. This comes from a simulation done at by the Princeton group about 2 years ago. And this is done with no neutrino transport, but just simple heating and cooling terms like the ones I have shown on the previous slide. What you see here in this essential cartoon, or sorry, in this essential graph, is on the vertical axis the neutrino luminosity just imposed from a lower boundary in this simulation. So it's a neutron star which is supposed to be the lower boundary radiating the neutrinos. And here you have the mass accretion rate. That means the rate of mass infall in the collapsing stellar core, the mass accretion rate onto the shock, damping the shock expansion. And what these two curves here show is the so-called critical conditions for an explosion. So when you are on this line for a certain value of the mass accretion rate, then you need this luminosity here in order to reach a runaway condition. The mass accretion rate is actually nothing else than a time coordinate. When time goes on, the mass infall rate onto the shock and onto the neutron star is decaying just because matter from larger and larger distances falls in, and therefore this density is diluting and the mass accretion rate goes down. So time runs that way. In a 1D simulation, you really need very high neutrino luminosities in order to get the runaway conditions and to get the criticality of the shock by neutrino heating. When you go to multi-D, and this was Hans-Walter Rick's question, the multi-D phenomenon is, or multi-D case reduces this critical luminosity just because it keeps matter in the gain layer for a longer time, and this material in the gain layer can then absorb energy from the neutrinos. This is a schematic graph obtained from a simple setup showing you the influence of a two-dimensional case compared to a one-dimensional case. So it reduces the required neutrino luminosities. Now, most sophisticated simulations are needed for the quantitative answer, and I will try to go into those ones now on the following slides. First, a few answers to what Hans-Walter Rix was asking. What is entering such models? Well, we need, of course, a lot of physics. We need hydrodynamics, magnetohydrodynamics of the stellar plasma. We need to take into account general relativity, because the neutron star is a very strong gravity source, and at least to an extent of 10 to 15% in the neutron star vicinity, the gravity is influenced by relativity. A nuclear equation of state for describing the hot neutron star matter enters neutrino physics, and also what matters is the conditions from the progenitors, which are given to us by stellar evolution groups producing the progenitor models at the onset of core collapse. This then is combined into what we model in the simulations, and then we get out a lot of diagnostic effects, neutrinos, gravitational waves, light curves and spectra, nucleosynthesis, explosion, asymmetries, pulsar kicks, and in the end also some systematics of explosion energies and remnant masses connected to the input models from on the progenitor side. So this is in a two-dimensional setup, a subset of equations we are solving. Subset for the following reason: this is first of all only 2D. We are now solving the three-dimensional case as well. Here you have the hydrodynamic equations in relativity, 2D general relativistic equations. Here you have the corresponding metric equations which we are solving in the so-called conformal flatness approximation, which is extremely good for the conditions we are investigating. And here you have the two moment equations of energy and momentum for the neutrino transport. And in addition to that, we also solve the Boltzmann equation in an approximate way in order to deduce the closure conditions, the closure relation for these two moment equations. I don't want to bother you with the details on the technical side, just so much for it. The problem is not the hydrodynamics. We are running three-dimensional hydrodynamical simulations, magnetohydrodynamical simulations, even relatively easily on computers nowadays. The problem is the neutrino transport. And the problem here is the fact that the neutrino transport is a 6+1 dimensional problem. You have 3 spatial coordinates and you have 3 momentum coordinates here visualized in this graph. And this 6+1, one is the time dimensional problem, cannot be solved on any computer nowadays. So where we are now in 2D and 3D is these lower yellow and red levels, where we do 2D and 3D hydrodynamics with what we call ray-by-ray plus approximation for the neutrino transport. It's time-dependent implicit neutrino transport, where we have a variable Eddington factor technique, and the ray-by-ray plus scheme is visualized on the next slide. What I mean by that, where we want to end up with is at this level, where we do the 3-dimensional hydro plus 6-dimensional radiation transport, but this is certainly bringing us into the exascale computing level. We need several hundred petaflops sustained. That means certainly the machines have to be much more powerful in order to provide this kind of capability in a sustained manner. So that is the ray-by-ray plus treatment. What we are doing, we solve the stellar model on a spherical grid. The hydrodynamics is done on a spherical grid, and the transport is solved along or in all of these angular bins. And we do a one-dimensional spherical symmetric transport problem with all of these rays. That means in the end, we're assuming that the radiation intensity, the neutrino intensity, is axially symmetric around this radial direction, but we fully take into account the angular directions here when we solve for the neutrino transport, and we fully take into account the energy dependence of the neutrino transport. What we need also to take into account is the essential core, of course, for dealing with the neutrino heating mechanism is a multitude of neutrino reactions which are responsible for producing neutrinos, but also for transporting neutrinos out of the neutron star. On the one hand, you have the charge current reactions producing electron neutrinos and antineutrinos by electron and positron captures on nuclei and protons and neutrons. You have scattering reactions of neutrinos, of nuclei, of neutrons, protons, and electrons, positrons. You have thermal pair processes producing neutrino and antineutrino pairs, and you have the pure neutrino reactions. All that is included in our simulations, which I think I can, without hesitation, call the state-of-the-art, the most sophisticated transport and hydrodynamics models existing at the moment. So now let me give you a brief overview of our results. Here we first consider, because they are particular, stars in the 8 to 10 solar mass range, so these are the lowest mass progenitors of supernovae. What's the particular property of these stars? Well, you see it here on this density radius slide. these stars actually have oxygen and magnesium cores and not iron cores, and the particular property, the particular characteristics of such cores is that they have an extremely steep density gradient at the edge of this interior core, which becomes unstable when electron captures on neon and magnesium set in. And this steep density gradient actually helps the explosion and differs a lot from the more massive iron core progenitors where the density profile is much more shallow. Yeah.
How do you treat the emerging neutron star? Is this a sync parting, or do you fully sort of compute the formation of neutron star and the spin up by means of the sort of emission of angular momentum in these simulations?
This is supernovae. There is no emerging neutron stars here.
No, but the former neutron star is central, right?
Yes.
And this will sort of get a kick by the sort of anisotropic emission of momentum. So that means basically spin up the neutron star.
Which momentum emission do you mean? There's a neutron star forming in the collapse of the stellar core, and this neutron star is...
So you don't spin this up, so you don't make a pulsar?
Well, this, of course, the neutron star obtains a certain angular momentum, or has a certain angular momentum, which it inherits from the rotation of a progenitor. But this rotation initially is relatively slow. So in some of the models we did in the group, it's included. It doesn't affect the explosion strongly. It makes a certain quantitative difference, but not a qualitative one. And in the end, when the ejecta of the supernova are accelerating outwards, you can spin up the neutron star by the angular momentum carried away in the ejecta. I will come to that point if time permits.
We follow this basically in the sentence.
Yeah, we do that. Okay, so here is the oxygen-magnesium core explosion which we obtain, and actually these explosions are the only ones which you can also get in spherically symmetric simulations, where you see here on this plot, it's a relatively technical plot, but relatively simple to understand if you know what you see. You see here the trajectories of certain mass shells. Here's the radius, and here's the time. So this is like a movie, this plot, showing you the collapse of the mass shells towards the forming neutron star here at the center, and on the other hand, the formation point of the shock wave travels outwards. It accelerates here at the steep density gradient at the edge of the oxygen and magnesium core, and then this shock wave is actually running into a successful explosion, and I think the devices don't like me because this one is also done and finished. Maybe it's just because I pressed too long, I don't know. Do we have some low-tech device? Try the other one again. Maybe this can recover as well. I'm sorry.
See how fast it can recharge a car battery.
Yes.
So you see these trajectories moving outwards, indicative of an onsetting explosion. So this was a result which we obtained a couple of years ago, already in a spherically symmetric simulation of an oxygen near magnesium core progenitor in the 8 to 10 solar mass range. And we ran this model later on also in 2 dimensions. You don't see a qualitative change of the explosion energy, so the 2D and the 1D explosion energy are roughly similar, but you see some convective instabilities for a short while. Then the explosion sets off and the asymmetry of the ejecta is imprinted. So at this time, of course, the asymmetries can also lead to some spin-up and to some kick of the neutron star. That is in the observational part of my talk, which I'm not really sure I will be able to cover at the end. Let us now try or ask the question, is this explaining something, or is this just a theoretical model? If you look closely here to this energy plot, you will see that the explosion energy is fairly low. It's of the order of 10 to the 50 ergs only, and not the canonical 10 to the 51 ergs of a supernova. So is this a meager explosion, or is it a healthy one? Well, already in the 1980s, there were speculations in the literature, conclusions drawn from observations that the crab may be an oxygen near magnesium core explosion. And the reason for that is that the Crab Nebula hardly contains any carbon and oxygen, and it has no visible amount of nickel, so it was concluded that it must be an explosion with very low nickel production, and also the kinetic energy of the crab is only several 10 to the 49 ergs, so a very, very low energetic explosion, and we think that this is very well matched by the numbers obtained in our models for the oxygen magnesium core explosion. So this seems to be an explanation for the graben. Actually, it has been, since we published the paper, suggested that some other supernovae, low energetic and faint supernovae, may also go back to such oxygen magnesium core collapses. Now let me go further in the mass space of progenitors and show you some results for iron core progenitors. This is an 8.1 solar mass iron core case for ultra metal poor conditions. This is a zero metallicity 9.6 solar mass star, and these are solar metallicity 11.2, 15, and 27 solar mass models run in relativistic two-dimensional core collapse calculations, and in all of those we obtain explosions. You can see that here in these diagrams. This is the radius coordinate, northern hemisphere, southern hemisphere, and we color code the entropy. And whenever you see the boundary between the bluish, low entropy, and the reddish and yellowish, high entropy regions moving outwards, expanding, it indicates to you a successful explosion. Let me show you a movie which is hidden below one of these plots here, just as an example, what you can see in a two-dimensional simulation. This is the 27 solar mass model which Bernhard Müller ran with his relativistic two-dimensional code, and you can see that there is a sloshing instability setting in, and this sloshing instability is actually the standing accretion shock instability before then also convection is entering, and you see a superposition of two different types of hydrodynamic motions, convective overturn motions on the other one hand, and convection on the other, and the Stasi instability on the other. Yeah, I have an explanation here on the Stasi phenomenon. Stasi is an advective acoustic instability. That means any perturbation created here by seed perturbations at the shock wave leads to some inward transportation in the accretion flow of vorticity, and this deceleration in the accretion layer of the neutron star then creates sonic waves. The sound waves couple back towards the shock, and then this cycle under fruitful conditions, under favorable conditions, can amplify and can steepen these non-radial motions into this sloshing behavior you have seen on the slide or in the movie before. This set of two-dimensional models where we obtain explosions is now increasing with Florian Hanke's PhD work, where he is now running a large set of models in 2 dimensions, spanning the mass range from 11.2 to 26.6 solar masses. Here I have another slide here from 16.8 to 28 solar masses. In all of these cases you see that at some point when the mass accretion rate is decaying to some sufficiently low level, the neutrino heating becomes strong enough to push the shock outwards and to initiate the explosion. So this looks really good. Summary slide on this part before I come to the latest results in 3 dimensions is that 2-dimensional models seem to confirm the basic viability of the neutrino heating mechanism, and we also confirm the reduction of the critical luminosity needed to initiate the explosion when you go to multi-dimensions, when you go to 2 dimensions. None of the spherically symmetric iron core progenitors is exploding. You really have to upgrade the simulations at least to the 2nd dimension in order to obtain the explosions. We have some quantitative differences compared to other recent explosion models in 2D published in the literature. We have to figure out where these differences come from. There's different numerics, but also different neutrino physics involved, and we need to collaborate on that. But now, the big issue and the big goal and challenge, of course, is the 3rd dimension. Why do we want to go further? Well, 2-dimensional successful explosion is nice, but you know that nature is 3-dimensional, and we have an artificial axis symmetry still in the simulations. 2 dimensions means that we assume axial symmetry around an arbitrarily chosen coordinate axis. And also we know, or we see that some of our 2-dimensional models only marginally explode, so that might change quantitatively, but we think in 3 dimensions. Another argument is that in 3D, the turbulent cascading is actually from the large to the small scales, different from 2 dimensions, where you have the energy transport from the small scales to the large scales. And another question was, is does this SASI phenomenon, which you saw in the sloshing motions along the symmetry axis of the simulation, also exist in 3 dimensions, or is it an artifact of the 2-dimensional setup? Well, I don't go into this. There was a claim by the Princeton group that 3D could even help to lower this critical value of the luminosity. We couldn't confirm that in a study, in a simple study we did a couple of years ago. But there's a growing diversity of first 3D results, some of them with a pretty meager treatment of the neutrinos. The Princeton group has recently revived its earlier result, and now they agree with our result of 2012 that in 3D the explosions don't seem to be faster and earlier than in 2D. Takiwaki, the Japanese group, even claimed that in 3D they found explosions setting in later than in 2D. Jean Couch confirmed their result, but both of these groups use gross approximations of the neutrino transport. Ott et al. Put out a paper in 2012 where they had re-investigated our 27 solar mass model in 3 dimensions and claimed that there is no neutrino, there is only neutrino-driven convection, but no SASI sloshing motions. So there is a growing diversity of claims in 3 dimensions, and we are now actually have started about 3/4 of a year ago to do full-scale 3-dimensional supernova modeling with all sophistications of the neutrino transport. I will make it. So this is a real challenge. Here you can see the challenge in 2D. With the resolution given here, we need about 1 million processor core hours to run a model. And this, of course, scales with the number of azimuthal grid bins, which we want to take into account. For 1.5 degrees resolution, you end up with about 100 million core hours you need. But thanks to a big computer time grant we got from the European Prize Initiative, about 150 million CPU hours, and now we have a proposal, well refereed, for another 150 million, which we mostly consume on the machine in Paris and the one in Munich. We could run the first 3-dimensional models now. Each of these simulations takes about 50 million core hours, so at the moment we have 3 finished 3-dimensional simulations. Requirement for these simulations is excellent scaling capability and tests on machines available to us for testing purposes. Up to 64,000 cores show nearly perfect scaling behavior of our code, so this is actually a demand if you want to be successful with your proposal. And here you see our first 3-dimensional simulation result for the 27 solar mass model, which I had shown you in the movie doing these violent sloshing motions. And let me, instead of going into the details of these 4 snapshots where entropy surfaces are shown, and here this outer envelope shows the shock, the supernova shock, let me show you the movie hiding behind this slide. Click it, and I will not. I will explain the essence only. Here you see the forming neutron star. Here you see the outer edge of the shock wave. This is already time after core bound, so when the shock has formed, the time is given in the upper right corner. And then you have the entropy scale here for the movie on the left-hand side, and yet you see this sloshing motion. This is the SASI for the first time also discovered in 3 dimensions. So we have confirmed the physical nature, the physics nature of the SASI instability in the supernova core. And then we continue the simulation for several hundred milliseconds more, ending in this movie at about 450 milliseconds after bounce, and you will not see any explosion. We continued for another 100 milliseconds, still did not receive an explosion, although the 2-dimensional model exploded. So the SASI, we discovered it, but we have no successful explosion in 3D. Let me give you a flash of the remaining 2 or 3 slides, which I definitely would like to show. There's not very much more. This is the SASI instability shown in a different way. Here we have another case. Here is this phenomenon in a very nice setup. The SASI instability in a cheap laboratory experiment developed by my friend in Paris, Thierry Fabrizio, in his garden. Actually, here you see the setup constructed in the garden. What you have here is a water reservoir fed in. These pipes here feed in water at the edge of this table in a roundish form, and the water is these pointers are really a mess. And you see that the water is flowing towards the center, and there's another pipe where the water can flow away. And this is a setup like the accreting neutron star. And if you increase the water inflow, then you will get this hydraulic jump, discontinuity in your water height. You can also find that in the sink of your water tub. And this is the equivalent here, the laboratory experiment, to the SASI instability. Let me show you the movies behind this slide. Here you have a setup where this shock wave, this hydraulic jump, stays spherical. So there is nothing which distorts it. It stays in a roundish way. Here you see another case where Jerry could get a sloshing mode. So it's just an increase of the mass accretion rate, of the water flow rate in this setup, which leads to the sloshing mode. And in the end, he could even obtain a spiraling behavior. However, he can't tell me what is the reason for exactly what are the conditions for getting this spiral mode behavior. So that's the way you can visualize and you can understand this instability. It's the same physics here in this experiment. Now, again, 3D explosions. As I said, the 27 solar mass model did not explode, while the 2D explosion was obtained. We did another simulation for 11 solar masses. Again, the same result. The 3D model looks a bit more promising for a while, but then in the end, the 3D model does not lead to an explosion, while the 2D model of the same progenitor explodes in the same setup. And here is a third simulation with the rest of the 50 million, the third chunk of 50 million core hours, which Florian could run for a 20 solar mass progenitor. And it seems that we get the same outcome, marginally failing to yield an explosion. So what's the problem? This is a summary slide, and then I'm ending. Well, in 2D, as I said, we have a relatively optimistic situation at the moment with a soft equation of state, and I don't want to quantify that further here. We obtain explosions for a large set of progenitors, but we don't get these explosions in the 3D case yet, but 3D modeling has only begun. We have rediscovered the SASI. The SASI is a physics phenomenon which really takes place in the supernova cores, but the 3D models are still relatively limited in resolution. The 16,000 cores which we have available allow us only for 2 degrees resolution, and this is probably not sufficient to get numerical convergence of turbulence of all these shear motions which we have in the flows. We have to go to higher resolution. And one of the issues which bothers me much is the spherical nature of the progenitors provided to us. The progenitor models are spheres, while they should have convective envelope, convective shells with a lot of perturbations. What we put in the models is artificial perturbations, seed perturbations, just random perturbations. This is probably not reflecting the true structure of the progenitors. So what in the end we have to hope to obtain, and one of my proposals is trying to go in that direction, is to obtain progenitor models which have developed, at least have been developed through the last stage of cell evolution in 3 dimensions. And of course always an issue and question marks have to be put here. Is there any physics missing? Thank you for your attention. I mean, maybe I ran over for 2 minutes or so, but I hope it was exciting enough for you to stay alert. Thank you.
So, any questions for Thomas? Young people first, sorry.
So I was trying to understand the reason behind the low kinetic energies in your 2-dimensional simulations.
Yeah, the main reason is that the 2-dimensional models tend to explode relatively late. And they always explode in our simulations when a shell, a composition shell, with a sufficiently large density jump arrives at the shock. This density jump leads to a decrease of the mass accretion rate, which is favorable for the onset of the explosion. Again, I remind you of the one last point here on the slide. If the progenitor shell structure looks a bit different, we can get a different outcome. So at the moment we have constrained our simulations to models which were provided by the Santa Cruz group, Stan Woosley and his collaborators. We're now trying to extend the modeling in 2 dimensions and some partially also in 3 dimensions to other groups' progenitors in order to explore whether their shell structures are more favorable for getting an explosion. But what's really crucial is how the mass accretion rate decreases as a function of time.
So you mean there is no dependence on the progenitor mass?
There is certainly I showed you that there is a strong dependence on the progenitor mass, but not even only that, there is also a strong dependence potentially on the groups providing the progenitors.
So when, for example, in two-dimensional simulations, is the neutrino transport also done in 2D?
Well, it's done in this approximation which I called ray-by-ray approximation.
Right.
What we do is we solve the neutrino transport on each angular grid bin in a spherically symmetric way. That means that we assume that the conditions in this angular grid bin are reflecting the conditions of a whole sphere. And in that sphere we solve a full transport problem by solving the Boltzmann equation in iteration with the moment equations. And there is coupling terms also for neutrino transport in the lateral directions. What this approximation essentially means is that the neutrino flux, but not the neutrino distribution in phase space. The neutrino flux is radial, or in other words, the neutrino intensity in phase space is axially symmetric around the radial direction. So
that's the two-dimensional assumption.
And well, you cannot, I mean, the transport is a six-dimensional problem.
Right.
So what you're doing is you reduce your dimensions by one. In 2D, we have 4 dimensions. In 3D, we have 5 dimensions, which we are solving for, but no, not the full 6-dimensional problem.
Right, but then how do you do bin by bin, angular bin on the one hand and the moment equation on the other hand? Are those two parallel approaches?
This is now very technical, and honestly, I don't understand exactly what your question is heading at. We can talk afterwards. Yeah.
Two questions, if I may. First is, can you identify a reason why the successful two-dimensional models won't explode in 3 dimensions? And the second question would be, suppose there are failed supernovae, what would they look like?
Both questions are viable. Honestly, really honestly, I don't have a good answer for the first one. Not yet. I mean, these results are very fresh. I mean, the first finished 3-dimensional run is about 3 months old. We are analyzing the data. We have a lot of plots, but all of these plots show that the 3-dimensional conditions are even more favorable for a certain while, several hundred milliseconds, 200 milliseconds, and then it seems to become less favorable. My tentative explanation for that is the suspicion that it's a lack of resolution. In particular, in the edges of these rising plumes, we have a lot of numerical viscosity still because we have a lack of resolution and we have a lot of numerical shear. And I would certainly want to reproduce these simulations with at least a factor of 2 better resolution. The second question is, what would a failed supernova look like? There are many answers to that. So the first is it would produce a black hole. And of course, it would, in the case of not significant amounts of rotation, it would eject only very little matter at the surface because the neutron star, then radiating neutrinos and accreting until it becomes a black hole, is losing rest mass energy in neutrinos. The gravity is reduced. And this leads to a puffing off of the surface layers. That has been studied in a renewed way by Lovegrace and Boosing recently, and also by Piero at Caltech. So this will not be like a supernova, it will be like an optical transient with low velocity expansion of material, reddish, very reddish. If there is rotation in the star would, a significant amount of rotation, the neutron star, and then the black hole will accrete matter until a torus forms. And then the speculation, of course, is that such collapses are linked to gamma ray bursts and these hypernova phenomena. But you need a lot of angular momentum, about a few times 10 to the 16th gram centimeter square per second, in order to keep material around the black hole, in an orbit around the black hole.
So is the density profile at the time when shock basically starts accelerates deeper than -3.2?
Well, essentially in these phases where the shock is pushed outwards, the density profile relatively closely follows an r to the -2 behavior because the cores in those regions are convective, and that flattens the entropy profile, and then the density profile is roughly like r to the -3. But when the matter reaches the shock wave, the density profile has changed into an r to the -1.5 profile. So the pre-shock density profile scales like r to the -1.5, while the progenitor profile scales in the static progenitor core scales like r to the -3, roughly. That has been actually analytically already recognized by Bede in 1990 or earlier than that.
I was surprised by your side remark that angular momentum doesn't matter so much.
Well, angular momentum.
My feeling is
Yeah.
it should not help collapse.
Well,
The extension is there have been some speculative ideas, among others by Wolfgang Heidelberg, that due to this rotation there are also not only one neutrino burst, but two.
well,
What's the
yeah.
status of that?
Yeah, I mean, there have been speculations connected to Supernova 87A, but I mean, well, I could give a talk on your question, so this is really difficult to answer. Short answer for your question on these speculations in the 1980s when Supernova 87A exploded. It's not shown in any model that you really can delay the time scale for hours in order to explain the 2 neutrino bursts in Mont Blanc, hours before the other neutrino bursts in Kamiokande, in Kamiokande and IB. So there has not been any model which can reliably explain this time scale. So I think this is not supported by any quantitative calculations. So the problem of angular momentum is of course among us, and it has been among us for a long time. It has been revived a couple of years ago, 10 years ago, in the connection of gamma ray bursts. Now we really think that angular momentum is strongly connected to the gamma ray burst and hypernova phenomenon. But stellar evolution modelers predict us that ordinary progenitors of 99.9% of all core collapses have slowly rotating progenitor cores, slowly rotating iron cores, just because they go through a red supergiant phase. In the case of a red supergiant phase, the star loses angular momentum, and this angular momentum loss is enormous. It decelerates the stellar core to a very low rotation rate. Typically, the progenitor cores of models given to us by stellar evolution modeling groups are rotating with periods of 100 seconds or more at the onset of collapse. This leads typically with angular momentum conservation to the prediction of pulsars with 10, maybe to 100 millisecond periods. If you have pulsars in their final stage rotating with 10 to 100 milliseconds, the influence on the explosion mechanism is very small. We explored this in simulations and we hardly see any bigger influence on the explosions. There is one but. We haven't done these simulations in 3D yet, and it may be that the spiral SASI, which is a phenomenon I showed you being present in 3D as well, that the spiral SASI has different growth rates in a rotating environment. There has been linear stability analysis showing that, and we want to see what happens if we put a little bit of rotation onto the progenitor core in 3D, but we haven't done that yet.
So I'm somewhat stuck with take-home message that after 150 million CPU hours, there's nobody on this planet who can make stars explode for the right reasons, right? And now, do the 5 question marks at the very end reflect how clear it is to you what to try next?
I have a list, a to-do list, what to do, and we will certainly not go to speculative ingredients of physics. What we need to do first is certainly we need to explore, with the next maybe chunk of 150 million core hours, we need to explore first, I think, a different equation of state. In 2 dimensions, it seems that a stiff equation of state is suppressing the explosion or unhealthy for the explosion, and a soft equation of state helps. It can be different in 3 dimensions. We need to assure the 2-dimensional result before we discard a stiff equation of state currently used in our models. The second is we have to try a little bit of rotation, just the same amount of rotation given to us by progenitor modelers in order to see whether the spiral SASI grows faster. And the third issue is we certainly have to simulate progenitors from other groups because their shell structure, the progenitor shell structure, may look largely different from what was provided by the Woosley models. Yeah? So I think the conclusion, and if you can lend me 1 minute more attention, I would be really pleased. Don't go out of this lecture hall and tell the supernova guys have a problem exploding their stars. We have just started to do the 3-dimensional models about 3/4 of a year ago. It took us a long way, maybe a decade nearly, to get the 2-dimensional models straightened out. Please give us at least, let me say, 1 or 2 more years in order to figure out what's going on in the 3-dimensional case.
Thank you. What role do magnetic fields play?
Yeah, that's a good question, of course. The main issue, I think, with magnetic fields is connected to rotation. If you have rapid rotation, then you will wind up magnetic fields on the one hand, but you will also get the MRI, the magnetorotational instability working. Also, you have an energy reservoir in the rotational energy of the forming neutron star, which can be huge. A neutron star born with 1 millisecond has about 5 times 10 to the 52 ergs. What you can tap is only the free energy of rotation. The same conclusion brings you immediately to the point that a neutron star born with 10 milliseconds rotates with a very low rotational energy, which never can explain an explosion energy. If you want to magnetically tap the convective energy, you are also lost, because the kinetic energy of convection is of the order of 10 to the 49 ergs. Again, not sufficient. You have to have an energy reservoir which you can tap efficiently, and if you want to invoke magnetic fields, then you really have to go to the rotating case, which I explained 5 minutes ago. It's only probably true for a subset of core collapse cases, maybe 0.1%.
So in your simulations, the magnetic fields don't actually do anything. I mean, you put them in, but in the end, it has no
they are not in here, but we have done simulations with magnetic fields. I have also published, there's a paper out from my group, where we have published 2-dimensional models with convection magnetic fields. We can only get them making something if we already use very strong magnetic fields in the progenitor core, about a factor of 1,000 higher compared to what is given to us by stellar evolution models.
Okay, the last 2 questions.
I have a completely non-technical question. Would you dare to show your omitted observational part to a particularly enduring subset of this audience?
Absolutely. It's prepared, it's finished, it's just another 20 slides. Lisa told me half an hour before I came here, not more than 45 minutes. Okay, so I
I'm very tough with these things.
Yes, please.
I was a bit surprised, and if I understood you correctly, you said from the modeler's perspective,
From the perspective?
from the
Modeler's perspective.
perspective of the models,
Yeah.
they are not good places for our process nucleosynthesis.
That's not what I said. Supernovae are no good place for an R process. That's what I said. For the strong R process, that's what I said. Supernovae. And there's 2 different R processes we see from the ultrametal poor stellar observations. You have a very unique kind of R process beyond mass number of 130, so of europium barium regime. You get a very unique pattern. Below that, you have a lot of scattering. It can be that or actually nowadays we think there are 2 different sources at least. The one may be connected to the production of the very heavy R process nuclei, and nowadays we think it's neutron star mergers. Actually, we have good models at the moment, and all groups doing that agree on that neutron star mergers definitely produce heavy R process material. The question only is it the only source, and is it the source also polluting the ultrametal poor stars? Supernovae may be, a subset of supernovae may be able to bring the light R process elements up to silver and palladium, but probably they can't do the heavier ones.
And I think with that, let's thank Thomas again.